Hello, we represent the Agile Locomotion and Manipulation team advised by Dr. Ye Zhao and Dr. Seth Hutchinson. A majority of the student team members work in the Laboratory for Intelligent Decision and Autonomous Robotics, or LiDAR. LiDAR is devoted to the novel development of legged robotic systems and robotic manipulation with industrial applications. LiDAR does design, software, and controls for multiple robotic platforms to advance the state-of-the-art in manipulation, locomotion, and collaborative engagement. The lab operates at both the high level, developing AI for task and motion planning, as well as a low level, developing benchtop sensor and control solutions. Athena is a biomimetic upper body being developed for joint locomotion and manipulation with Cassie, a bipedal walking robot, as a lower body. Designed as an affordable tool to increase access to the robotics and control space for research groups, it demonstrated success through the Advanced Intelligent Mechatronics 2020 poster competition and is now improving the platform for locomotion and manipulation research and development on the Cassie biped. There are many robotic gripping solutions on the market, but most contain high entry costs. In addition, they can only be used on a table due to a large control box that must come with the arm. Athena will provide a more affordable and mobile path in the manipulator controls field as a stationary or mobile dual-arm solution capable of collaborative tasks. Athena's cost and performance can be attributed to multiple innovative techniques that were used in the design process. Structural elements of the 15 degree of freedom system utilize topology optimization, a computer simulation method that generates complex geometries to optimize the strength-to-weight ratio. The geometries are realizable with 3D printing and composites for a lightweight and high-performance design. These benefits are compounded with Athena's remote actuation scheme, which reduces the inertia of its arms, reducing the energy needed to move the system. Rather than relying exclusively on hardware solutions for a safe design, we designed high-bandwidth motor transmissions with software-based virtual compliance to dramatically cut the cost of production. Most robot actuators are expensive due to their large transmissions and internal mechanical devices that must be precisely machined. For instance, series elastic actuators are commonly used in collaborative robots but use large, expensive gearboxes in combination with a finely tuned spring to achieve a compliant response. The spring allows the system to absorb energy and not harm or damage any people or objects it comes into contact with. This is not only expensive but inefficient due to losses in the system. Athena uses larger brushless DC motors and small gear reductions, which has less loss in the system and provides more control authority for a low cost. Impedance control is a force-based approach that models the robot joint as a spring. Through this control method, we can achieve similar compliance, safety, and utility to mechanical springs while reducing the cost and complexity of the overall system. Traditional robot arms suffer from heavy motor systems on their joints with large gear ratios. This reduces the maximum speed and torque of the joints in addition to making it more difficult to control. The Athena arm avoids these drawbacks by moving most of the motors to the shoulder, decentralizing the actuator systems. This reduces the inertia of the system, resulting in higher agility and control authority. There are no pinch points on the arm, which means the robot will be safer for humans to interact with than many other robot arms on the market. Like most collaborative robots, each arm has a sensor and control for robot position, velocity, torque, and acceleration. Also similar to other collaborative robots, a single Athena arm is only capable of lifting a few kilograms of weight, but the two arms together enable it to manipulate objects that are significantly more difficult to lift and control. The Athena wrist uses a remote 2 degree of freedom differential drive mechanism to achieve a lower inertia in the forearm. This lowers the overall power needs of the robot and helps reduce costs and increase performance. A custom PCB was developed to control the DC motor transmission. Each finger has a linear actuator on the forearm for independent articulation. Shown here is a simulation with a basic gripper end effector involving a simple pick-and-place operation. A large disturbance force is applied to simulate contact with a human, showing that the robot can safely operate despite the environmental disturbance. This will eventually transition into full-body control solutions for both of Athena's arms. The Athena body is an innovative and novel design that increases mobility and dexterity for the entire system. It includes a 3 degree of freedom spine system that has an independent forward and backward pitch, as well as a yaw axis rotation in the base. This allows for dynamic control of the center of mass, which assists in efficient object manipulation and balance. Weight is a large challenge for the system because of its low cost. To reach these low weights, material is eliminated in non-vital regions while maintaining the strength of the original part. The Athena upper body is a flexible platform for research groups and thus has a set of modules to fit many manipulation requirements. For perception, Athena uses a Stewart platform to track and follow different points in space. This module is infrastructure for a head attachment to aid in perception research. Athena also has a set of grippers, including a fully actuated hand that can be used for finer manipulation with greater repeatability. That is all. Thank you for your time and consideration.